Hello everyone, my name is Todd Mackenzie, and today I'm going to present the results of monitoring the settlement, tilt, and tilt direction of Millennium Tower using INSAR. Millennium Tower is a 200-meter tall residential skyscraper located in San Francisco. The building opened to residents in 2009, and in 2015 it was disclosed by the developer that the building was sinking and tilting. This led to several court cases among multiple parties, one of which hired 3V geomatics to analyze the building motion using INSAR. We used two TSX stacks, one ascending and one descending, with data going back to 2009 when the building opened. Shown here is a line of sight displacement graph from the descending orbit for one of the thousands of data points on the Millennium Tower. Interpreting line-of-sight displacement results in terms of building settlement, tilt, and tilt direction are not straightforward, so we developed a building model. The tower model we created assumes that the building is a rigid structure that can move up or down and has a pivot point that's located just beneath ground level. No rotation around the z-axis is allowed. With these assumptions, we were able to derive a formula that predicts the line-of-sight displacement for any point on the building and is parameterized by the motion of a single point located at the top of the tower. With this model, we've performed least squares fitting to the thousands of data points located on the tower and were able to derive the motion parameters of the building. Shown here is the vertical displacement of the tower, along with the vertical velocity over a period that starts in 2009 and ends in 2018. The three results shown here are the model fit to just the ascending data, just the descending data, and to both data sets simultaneously. The agreement between the ascending and descending results are quite remarkable. Missing in the previous results are the uncertainties. Uncertainty calculations when using INSAR are challenging due to many factors involved. Particularly challenging is the fact that neighboring points on the building are correlated due to residual atmosphere and filtering, making propagating uncertainties into the derived motion parameters challenging. To overcome this difficulty, we chose a rather unique approach. Surrounding Millennium Tower are 57 other tall buildings with dual TSX coverage. We made the assumption that these buildings are stable and injected the expected motion signal from Millennium Tower onto these other buildings. By then fitting our model to these other buildings, we can analyze the results to estimate our uncertainties. These are the same results that were shown before, but now include our uncertainty estimates, which are 95th percentile limits. As you can see with our combined results, uncertainties in the vertical settlement are less than a centimeter over the 9-year period. Shown now are the results for tilting of the building. This is for a point located at the top of the Millennium Tower. The uncertainty of the tilt for this point is 3 centimeters, which translates to an uncertainty in the angle of the building of 1,000th of a degree. The previous results showed tilt but lacked directional information. This here is an animation of the tower tilt over the 9-year time frame. Again, this is for a point located at the top of the building. It's interesting to note how the direction of the tilt evolved with time. The work shown here demonstrates that with a single INSAR stack, we're able to derive the settlement, tilt, and tilt direction with very good accuracy, as well as derive accurate uncertainties for those measurements. Because of this, these results were chosen as a reference data set for the court proceedings over other more traditional methods. New skyscraper construction is guaranteed, and the work here demonstrates that INSAR is the best tool for ongoing monitoring.